Right. So because I just started recording, so the subchapter I'm proposing is the full sky 21 centimeter survey on dipole anisotropy, 21 centimeter ISW, and then maybe also detecting the monopole out of SKA, and then because there is an idea that if you have short baselines, then interferometer becomes responsive to the monopole because
Yes.
yeah, right. Yeah,
I
there are those.
understand.
Yeah, there are those ideas. So and then probably what we are seeing, what we will see today from Minji's Oscar result might be just doing that. It's just unexpectedly. So that might also go into that subchapter, but I don't know. Yeah. So we'll see. So yeah, just let's then start the telecon. So I don't see any people from the Europe or Australia. So I think this will be it. So Minji, could you share the
screen?
Sure.
Okay. Yeah, can you see my screen?
Yes. Yeah.
Okay.
So the first agenda is just she will go through the progress she made so far with running the Oscar, and then I also have some inputs on what she got, and then so yeah, Minji, please go ahead.
Okay. Yeah, I make one slide, which is kind of showing some overview about what I have done. So I hope I can hear some useful comments from any of you, because I don't have much experience about data in radio astronomy. So what I did is first, based on the ISW angular power spectrum, we made sky model. So this is what it looks like. And it is a input for making the interferometer simulation using Oscar. So using this input, and you can see some options that I choose for observation setting and interferometer. Here, for the sky model, this file is exactly what I showed here. And then as the SDC3A did, I chose the phase center at 0, -30 in terms of RA deck. And this is the start observation time and for 4 hours. And we have 5 steps in time. And because we are interested in very low L information, I used filter from 2 to 40 in terms of the UV mode. So this is the visibility. No, it's not visibility. It's the UV number of mode in UV plane. It's density field. And if we shrink this 2D information into one, and this is what we have, the number of mode along the UV distance axis. And this is the visibility amplitude. Because it's a complex number, I just took the amplitude of it and then plot it along the UV distance. And Oscar has also the image option, so that using this visibility data, we can make image from it.
Yeah, that's not the visibility data. That's just the UV.
Yeah, right. Yeah, right. So using the output of this interferometer simulation, we make image. So because we are very interested in large scales, the field of view is pretty large, 90 degree. And it seems Oscar provides a couple of options for the image, like for the algorithm we have like FFT, simple FFT, or discrete Fourier transform 2D, 3D, and W projection is one of them. And since we are dealing with very large scales, I think this is the option that we want. And for the weighting, there are natural weight and uniform weight and radial weight. But again, since we are very interested in large scales, I think natural weight is the one that we want. And this is how it looked like. So
can I go through this
yeah,
once
sure.
again?
Yeah.
Right. So on the sky model, we thought that because Milky Way is just too strong, as a start, we just wanted to input the ISW only. And then the monopole signal is mostly the CMB plus the delta TB. And so we first chose one frequency sky. So the frequency, as a frequency, even as before, we just chose 100 megahertz.
Yeah, right.
So just one frequency at the moment. And then so this color bar is it's just a 2.6 something. So mean is 2.62. I cannot see the number correctly. 49 something, and then and then the max is 2.625 or something. Yeah, so you have a RMS about some tens of microkelvin against the CMB and the delta TB monopole. Because could you, Minji, go to the slide 16?
Okay.
Right. So here we have two choices. One is the x-axis is the frequency, and y-axis is the delta TB, the differential brightness temperature of the monopole. And then the blue is just the usual monopole signal. So it is, as you well know, it is just absorption at high redshift and then slight emission at the low redshift. And because we have to add this to the CMB temperature, 2.7 Kelvin. So 2.7 minus 0.2 is just something like 2.5 or something. So that's the mean number you see, and then the fluctuation comes from the ISW we calculated, and then it is just such a tiny fluctuation. So it is
0.1 Kelvin, around
0.1 millikelvin.
A millikelvin. Okay, yeah. It's
so it's really,
okay.
really small. Yeah. So RMS is just because I mean the point two, like here you look at the 100 megahertz, you have minus 0.1. I'm sorry, right? So minus 0.1. So that's why your mean is fluctuating around 2.6 Kelvin, not 2.7 Kelvin, right?
Yeah.
And then the actual RMS of the fluctuation is only about tens of microkelvin. Or 100 micro. Yeah, I'm sorry.
Why?
100 microkelvin. I'm sorry, not 10 microkelvin.
Yeah, y-axis is Kelvin, not millikelvin.
Yeah. Millikelvin. Yeah.
Yeah, millikelvin, sub-millikelvin fluctuation. So it's awfully small. Yeah, but signal is just there. So we just wanted to see whether this will be reproduced by inputting this guy to the Oscar and then getting the visibility and then get the image back and see if we have the input.
So you assume some dark energy model to calculate this as
It is just at the moment it is just the lambda CDM.
Lambda CDM.
Yeah,
Okay.
not the not the
fancy.
yeah, Chaplin or those things.
Yeah.
Yeah.
Okay.
Right. And then so that's that. So that's the input, and then right then so the output does not look like the input. So can we go back to the original slide that you showed, Minji? Yes. Right. So just I asked Minji to just use the very large field just as a practice. So we set the field of view as 90 degree, whatever that means. So here the field of view is
I confused here
yeah.
because in middle panel you said the
Mhm.
face center is -30 and the length is 4 hours duration, right? Observation.
Right.
So that means it's just a small patch of the sky because this is a drift. I think the drift scan. It's a fixed the
Right.
pointing fixed
Yeah,
on
yeah. Tracking. Yeah.
Yeah, it's a tracking, not
Right.
drift scanning.
Right.
So but in the right panel you said 90-degree field of view. I think it's a contradict. So
Yeah, yeah. Right.
maybe they have small patch, but you project to a very big flat surface like
Right. Yeah, maybe. So
I
this
think you
this
have assumed the beam pattern, right? Beam pattern in Oscar, you need the beam pattern. Usually for the maybe I think 20-degree that is assume a Gaussian beam
Mhm.
width. Sigma is
I see,
forgot.
I see. So okay, Minji, so what Lu says is this is field of view, not the
Real, yeah,
not the actual sky target sky.
yes.
Target sky size is different from the field of view. Field of view is the beam size basically in angle.
Yes, I think so. Yeah,
Right.
yes.
Okay, so does that mean, I mean, depending on the duration of the observation,
No.
this
It
number?
It's
is determined by the antenna shape. You know what the antenna looks like.
it's a primary beam, so determined by the dish size.
Yeah, dish size. You're right. Yeah, so smaller the dish, the larger the field of view. And
Okay, so
But in the SKA data challenge 3, they have already provided this beam pattern, I think. Yeah.
Right.
You can directly use this beam pattern.
Good.
yeah.
That's a good input. Okay.
So
I think it's also input. I think it's input when you generate the visibility. In this interferometer simulation, I think there must have one option you can choose to determine the beam pattern. Also, yeah, some file, read the file to
okay,
simulate it.
yeah, I think to get some very direct comments, maybe we can share this one.
Yeah.
So okay, so here we have SIM interferometer in Oscar, and it has these kind of settings. Overall, it's about sky model and observation.
This is tracking. Okay, this is tracking. Okay.
There's a trick. There's observation mode tracking. I see.
Yeah, and we can choose drift skin.
Drift skin. Yeah, we have to do.
Yeah, but now is a tracking, so you fix the patch on the sky. Yeah.
Okay. Then what would be the usual observation mode for real SKA? I mean,
No, it depends on your science.
Yes.
If you want to focus on the fixed patch of the sky, then you have to do the tracking. And if you want to, as our case, if you want to do the full sky, then you have to do the drift scan.
I have to choose this one.
Yep.
Okay. Oh, that's very useful. Yeah. comments, I think we should go with this.
Yeah, and then the
Gift.
one thing then, because Luke has cleared, the field of view input here is as Lu and I am saying just, it is just the beam pattern.
Beam pattern.
Yeah, determined by the
Yeah, you
shape.
said the aperture setting.
Yeah.
Yeah, I think it has such aperture array setting here.
Yeah, yes.
Oh, wow.
Now, one thing we have
Yeah,
to.
this one. I think is this one. Yeah.
And here, what should I do? I mean, so many options.
This is systematics. You just assume 0. Yeah, I think so. The gain arrow, x element, standard position, standard deviation.
So
I
this
think
is
the first
something
one
we can ask Kath, because yeah, I mean, because we know we have to input the beam made by like several antenna arrays, because we are forming the small baseline, right? So
Yes.
the substation, we substation it, so each substation has its own beam pattern. And we have to ask Kath how to just
You can choose the Gaussian beam, I think.
yeah.
Not aperture.
Yeah, it's just approximately.
Yeah, you let us first try the Gaussian beam. Maybe you can click it.
Okay.
We can look at
Okay.
what's going on.
Okay. Gaussian beam. Yeah. So what's the difference? I mean, Gaussian is
No,
there
it's
is
just approximation. Just approximation.
okay.
Yeah, usually it's like a Bessel function, not a Gaussian. In the realistic beam pattern, it's not a perfect Gaussian.
You mean aperture
You
array
have-
is Bessel?
Yeah, you have to simulate it because of the first application. Maybe you can simulate the beam pattern. You can
Yeah,
click
right.
the first
Yeah.
Yeah, you can simulate beam pattern. So this is like we said they simulate x and y direction of beam pattern, as realistic as possible to
Okay.
not a Gaussian. Yeah.
So you are
I
suggesting
remember in the SDC3 data challenge, the beam pattern, I think they gave the provided the patch about 10 degree. 8 degree. I think actually it's 8 degree for each side. So the 8 by 8 degree squared is patch. And they assume a Gaussian. Yeah, in this patch, they assume a Gaussian. I think the Gaussian, basically the Gaussian beam pattern. Yeah.
Yeah, just the one thing I'm worrying is that because we just made a small stations. So
Yeah.
if
But the problem is in practice, because for the UR detection, usually we look at a small patch where the foreground contamination is minimal.
I know.
We have to choose not a very big patch, otherwise the side lobe and other galactic plane. Yeah. That's why in the DC challenge, we only they choose this like 10 by 10 this degree patch, small patch.
Yes. Yeah, we know that. Yeah, it's just that this science is just beyond 10 degree. So that's why it is just we are just testing whether it is even feasible. Basically,
You signal, what's the coherent length of your signal on the sky?
larger than 10 degrees.
Or larger than 10.
Yeah,
So I think 20, maybe 20 by 20 is okay. I think 20 by 20. If too large, I think there would be very strong foreground.
Yeah, so that's the biggest worry. It's just when we wrote the paper, we kind of estimated that, because if you do the cross correlation, then the Milky Way structure should not correlate with this ISW pattern in principle, right?
But
In principle, yeah.
on average, right. But you have
Yeah, you have
infinite
accidental,
realization.
yeah, you have accidental correlation, right? Yeah, so
But the chance correlation is strong because even in theory there's no correlation, but in this
yeah,
one realization of the foreground and the signal there is strong chance correlation.
yes,
You
yes.
cannot remove it. Yeah.
Yes. So yeah, I was also thinking, if you have that kind of correlation, then you can just use it, and then later you can also imagine removing that foreground by
Yeah,
spectral
you have
smoothness.
to first remove the foreground.
Yeah,
But the residue, the foreground residue maybe have very small correlation with the signal.
yeah,
So
yeah.
that's why you have to choose the cleanest sky patch,
Right.
not the full sky. Otherwise, I think the full sky is
Yeah, first
too
guy is just
aggressive.
right. So yeah, I'm terribly worried about it, basically.
Full sky maybe increase the signal to noise because cosmic variance, but I think I still thinking about the foreground residue maybe much larger than the cosmic variance.
Yeah, I agree. So that was always the case, actually. That's always. I mean, it depends on the frequency, and then when I estimated it, I just did the usual Gaussian type of residual. So if you just using the radiometer equation, and then what would be the photon shot noise, and then that was sort of treatable at like 100 megahertz. Not at redshift of 30, but if you go to redshift of 20 or less, then it was kind of treatable. So that's why, yeah. But then actually, because Milky Way has such a strong structure,
Yes,
yeah,
yeah.
like
Also, you
that,
have the extragalactic point sources that's actually very strong.
yeah.
Even it's a point source, but you can mask it out, but some diffused unresolved point source also very strong, I think.
Right. So, but still, X scale, if they are if they form the diffuse background, then you also expect that they also will be spectrally smooth, so you can kind of,
That's true. That's true. Yeah.
right. So, it's the same thing. Yeah. Basically, if you can remove the foreground, then you are removing both the Milky Way and then the X scale component. That's the, even though in the paper we just showcase that the Milky Way and then ISW is completely uncorrelated, so you can just remove it naturally. So that was my,
Okay.
yeah, but in reality it may not. So the one other thing we want to show is that so let's say that, yeah, so this yeah, probably. Yeah, but before the visibility, yeah, let's go to the third one. Yeah, third one, yes. So here you have on the upper panel, you have V, so that's the vanilla. So the monopole delta TB goes to something like 200 millikelvin, very typical, right? Absorption depth. So in lambda CDM type 1. And then the next one is edges like 1. So it goes to 500 millikelvin. Yeah, if you look at the blue line. Yeah, so just scale is different. So that's we call it non-standard or edges-like. And then what you see out of the whatever you do, W projection or whatever, the image you get out of both the V and NS, they have to be about like 5 times different, or about 2.5 times different, something like that, because the ISW effect becomes stronger for the NS. So RMS is much larger. For compared to the V case, ISW, let's say the RMS is, did I say 100 millikelvin? If it is 100 microkelvin, then here it will be like, 250 microkelvin RMS. But what we get out of this is just they look almost the same up and down. If you look at the color bars here and here, then they look almost the same, slightly different. So now I'm not sure whether this is just the effect of using tracking or whatever. But anyway, I thought that this is unexpectedly, it might be just responding to the monopole, because we are using the short baselines. So that was not what I wanted to see in the first place, because I wanted to see the ISW, but now, because the baselines are quite short, then it might just respond to the monopole. And then because the monopoles are about the same, then we may be looking at it. So I don't know.
I'm not sure because
I hope not.
yeah, I hope not. Yeah, because the monopole actually the leakage to the short baseline
Right.
I think very small.
Yeah. Okay. Right.
So use the interferometer to probe the monopole, I think it's still hard because
Okay.
it's how to say it's a counterpart intuition, right? So because you use baseline to because it's just because the sky is a curved sky, so they have this effect. If the flat sky actually there's no leakage from the monopole to the UV to the baseline actually. Yeah. So I confused. What's the V and NS here? V means V and NS.
Yeah, maybe we can see this one.
Yeah, V is the vanilla. So in the lambda CDM, yeah, in the lambda CDM, you usually the 21 centimeter global signal goes to like 200 millikelvin dip.
Okay.
Yeah, if you're familiar
Oh,
with
it's a V. Okay, it's called a V.
monopole.
Okay.
Yeah. NS is just like edges. Edges has seen 500 millikelvin dip, right?
You just
yeah, I just stretched it to 500 Kelvin.
Okay,
So
increase
then,
the peak. Okay.
Right. So ISW gets stronger for the NS, of course, because it is ISW is modulated by this monopole signal, right? So because we tested 2 different skies, you input 2 different ones, then we expected that the reconstructed image out of Oscar will also have that kind of factor, but we don't see that factor. So that's why I say, oh, is it just responsive to the monopole? That's our guess.
Did you simulate the noise in Oscar?
No, I don't.
No, it's just seeing everything ideal at the point. So step by step, no way, no XGS, no point source, just clean, very isotropic sky, but with a very small, tiny fluctuation due to ISW.
Okay, but I didn't see where we can choose the noise in this Oscar
I
pen
think
is
I think we
this is
do have,
this
yeah.
okay. The false system noise. How to close this white noise for each baseline? You noise seed, okay. Enable, okay.
So can I ask why you want to care about noise? I mean, maybe something in your mind.
No, I think the plot, because maybe noise can, in this figure, in this image, in your simulation, Oscar simulation, because you only observe 4 hours, I think the noise is very large. Because in the SDC3, they simulate 1,000 hours.
Right.
So they repeat 4 hours observation 250 times. They repeat this. But here you just maybe you close the noise. But if you simulate the noise, I think in the image domain, they're much maybe the signal would be smaller than some signal would be smaller than the noise. That's why they didn't see the fluctuation. I mean the level as you expected.
But I didn't turn on the
You didn't
system.
turn on, okay.
Yeah, I
okay.
just make it false. So
False.
yeah,
okay.
I think we don't have system noise here. Yeah, so I think there must be some physical reason. Or
did SDC3A team actually did the multiple simulations and then add them up, or did they do one simulation and then just scale the noise? I'm not. I mean, you can sort of imagine that because it is just tracking,